So far this week, we have discussed how to solve Laplace's equation. And the method for solution that we have used is separation of variables. And we have discussed solution in Cartesian coordinates, in polar coordinates, and spherical polar coordinates. In 2 dimensions. In this lecture, I will solve one problem of each kind to give you some practice on how to solve these problems using these methods. Problem 1 is taken from Zangwill's book, 7.9 problem number, and it says 2 flat conductor plates which are infinite in extent occupy planes z equals plus minus d. The x greater than 0 region of both plates is held at potential phi 0 and x less than 0 region at potential minus phi 0. What we are being asked to do is to obtain the expression for the potential between the plates. So, let us see what does the situation look like. You have been given these plates at z equals d and z equals minus d. The direction to the right is x, direction upwards is z, and perpendicular to this plane is y, and on the right side both the plates are at phi naught, and on the left side both the plates are at minus phi naught. We want to find the expression for the potential in the middle of the plates. If you recall the solution, we had written that V x y can be written as summation some m a m sine some k m x plus b m cosine of k m x times the function I am going to write C m cos hyperbolic k m y plus dm sine hyperbolic km y. That's one way of writing the solution. The other way could be that I write V x y as equal to summation m a m sine of hyperbolic k m x plus b m cosine hyperbolic k m x times c m sine of k m y plus d m cosine of k m y. Both are valid solutions, and we choose a solution that is appropriate for our problem. Notice that in this problem, the potential is odd around x equals 0. Right? So, number 1, V x is odd about x equals 0. And number 2, it is finite and the same, and therefore, even about z equals 0. And therefore, it is very clear that the solution I should choose would be the first one. That is just from the symmetry of the problem. Even if you wrote everything clearly in the first solution and then to carry out the integrals, you will find that it will pick up the right terms, which I am going to now just state and use. But it is very clear that it is better to use the first form, because sine k m x has the possibility of giving me odd solution in x, and cosine hyperbolic k m y has the possibility of giving me a same symmetric solution about z equals 0, which is finite at both z equals plus and minus d. I should have mentioned that it is the same at z equals plus minus d. So, the solution that I choose is going to be V x z, is going to be summation some constant a m sine of k m x cos hyperbolic of k m z. Why? Because again, solution is odd about this, the x part, and is the same at plus minus d, and is even about plus z equals 0. So, this is z equals 0, it is even. So, this is the best solution. As I said earlier, even if I wrote the full solution out, I will pick up non-zero terms, which are only with this product. Now, here x goes up to infinity. So, instead of the sum, the solution should be written actually as a Fourier series. So, this is going to be actually integration over k, a k sine of k x cos hyperbolic of k z. This is the true solution, because x boundaries are at plus or minus infinity. So, x boundaries are at plus minus infinity. So, this is a Fourier series solution. And you do the inverse Fourier transform and you can get a k. But I am going to solve this, that is the standard way of doing it. I am going to solve it taking the size to be finite and then taking that limit going to infinity, and you will see how I can generate the same solution. So, it will teach you something new about handling these infinite distances. So, what I am going to do is take this problem to be like this, that on the right hand side I will make a boundary at L, on the left hand side I will make a boundary at minus L, where L tends to infinity. And when L tends to infinity, you will see that I can replace the summation by an integration. So, then the solution I am going to write is again like in the previous form, that is V x z is equal to summation m a m sine k m x cos hyperbolic of k m z, and let us take V x is equal to 0 at x equals plus or minus L, and therefore, K m is going to be m pi over L. This implies that I can write the solution as, this is the problem, V x z equals summation m equals 1 to infinity a m sine of m pi over L x cos hyperbolic of m pi over L z. That is my solution. And by using the boundary condition, I can now find what a m's are. What is the boundary condition? It is that at z equals d or minus d, it is even, so it does not matter, the V x d is equal to phi naught for x greater than 0, and V x d is equal to minus phi naught for x less than 0. I will just consider x greater than 0 side, because this minus and plus signs I have already taken care of by choosing sign. If I had chosen cos also in the solution by this plus and minus thing, I would have eliminated the coefficient for that term, that is, that coefficient would have come out to be 0. So, I can now write that V x d is equal to summation m equals 1 to infinity a m sine of m pi over L x cos hyperbolic of m pi over L d. This is for x greater than 0, and this should be equal to phi 0. Now, let me multiply by sin n x on both sides and integrate to find a m. When I do that, I get integration phi 0 sine of, not n x, this is k n x. So, this is n pi over L x dx 0 to L is equal to summation m equals 1 to infinity a m sine m pi over L x sine n pi over L x dx 0 to L times cos hyperbolic m pi over L d. In one of the previous lectures, I had asked to show that this term is actually L by 2 delta m n, and therefore, I get integration 0 to L phi 0 sine of n pi over L x dx equals a n L by 2 cos hyperbolic of n pi over L d, and that gives you a n. So, we have phi 0 integration 0 to L sine of n pi over L x dx equals a n L over 2 cos hyperbolic of n pi over L d. This integral 0 to L sine n pi over L x dx is nothing but L over n pi cos of n pi over L x 0 to L with a minus sign in front, and this is going to be equal to L over n pi 1 minus cos of n pi, which is equal to L over n pi 1 minus 1 raised to n. So, the left hand side is 0 for n even and is equal to 2L over n pi for n odd, and therefore, I get a n is equal to 0 for n equals even and a n equals 4 L phi 0 over n pi cos hyperbolic n pi over L d for n odd. So, we have now found our solution. The solution is going to be V x z equals summation. I will put odd ends directly. So, I am going to make this m equals 0 to infinity 4 L pi 0 over 2 m plus 1, that makes it odd, cos hyperbolic of 2 m plus 1 pi over L d times sine of 2 m plus 1 pi over L x times cos hyperbolic of 2 m plus 1 pi over L z. That is your answer. I am now going to change this to an integral by taking k m to be equal to 2 m plus 1 pi over L. Delta m equals 1. That means, when I go from 0 to 1 to 3 to 4 implies that delta k correspondingly is 2 pi over L. K is only 2 m plus 1 pi over L and delta k is 2 pi over L. So, let me collect all the terms and write the answer correctly. So, if you look at this, I had this phi naught sine of n pi over L x dx 0 to L is equal to a n L by 2 cos hyperbolic of n pi over L d, and this term after integration I got to be non-zero for odd n, and its value came out to be 2 L phi 0 over n pi. and therefore, a n L over 2 cos hyperbolic of n pi over L d is equal to 2 L phi 0 over n pi. L cancels from both sides, and I get a n to be equal to 4 phi 0 over n pi cos hyperbolic of n pi over L d. I can now substitute this in the solution and write my answer. I'll write this taking care of the fact that n is odd as v x z equals summation m equals 0 to infinity 4 phi 0 over 2m plus 1 pi cos hyperbolic of 2m plus 1 over L pi d times sine of 2m plus 1 pi over L x times cos hyperbolic of 2m plus 1 over L pi z. Now, you see I am going to write, as I wrote in the previous slide, that K m is equal to 2m plus 1 over L times pi, and delta m equals 1 implies delta k is equal to 2 over L pi. So, let us write this summation as an integration, convert this into integration by writing v x z equals summation m equals 0 to infinity 4 phi 0 over 2m plus 1 pi, is divide by L, multiply by L, cos hyperbolic of K m d times sine of K m x times cos hyperbolic of K m z. This quantity itself is K m. So, this comes out to be summation m equals 0 to infinity 4 phi 0 over K m 1 over L, this is this term, 1 over cos hyperbolic K m d times sine of K m x cos hyperbolic of K m z. I am now going to replace this summation m by delta k. So, it is actually summation over k. Delta k is 2 pi by L. So, it is going to be phi 0 2 over K m pi, and let me write this as 2 pi by L and the rest of the terms. This is nothing but delta k tending to 0 as L tends to infinity, and therefore, I can write this whole thing as integration 2 phi 0 over pi k dk sine k x cos hyperbolic k z over cos hyperbolic k d. That is my answer. So, v x z is given as 2 phi 0 over pi integration dk over k of this sine k x cos hyperbolic k z over cos hyperbolic k d. I have gotten it through taking a large box and taking all the limits. You could have done it directly by writing the Fourier series and Fourier inverse Fourier transform, but I thought I will just go over this in so much detail, so that you also learn how to deal with boundaries that are at a far, far distance. For problem 2 is taken from Jackson. This is problem number 2.26. It says that you are given a wedge-like portion in the xy plane, and this extends in the z direction up to infinity. So, z direction is extension from minus infinity to plus infinity, and this is the region with given this boundaries phi equals 0, phi equals beta, this distance is s equals a, and the potential here is to be found as a function of s and phi. You are given that the boundary condition as far distance is given in some form. So, I could actually have something like this region where I have been given v equals 0 here, v equals 0 here, v equals 0 here, and v equals some v phi at s equals, let us say, b. That could be one possibility, and I want to find v s phi in this region. There could be other possibility that this could be a constant. Whatever it is, I mean, what we want to find is, given this problem where the potential is 0 at phi equals 0, at s equals a, v is 0, and at phi equals beta, also v is 0. Then what is the potential in the region in the middle if somewhere far away the potential is specified? That is the problem. So, for the solution, we know what the solution is, v s phi. We have written the full solution as a phi plus b from c plus d log s plus summation m a m sine some k m phi plus b m cosine k m phi times c m s raised to k m plus d m s raised to minus k m. This is the full solution, and we need to pick the right things, or they will come out automatically when I apply the boundary conditions. So, application of boundary conditions gives the coefficients. But right now, I am just looking at the problem, I can make out what the coefficients are going to be. So, since v is 0 at phi equals 0 and at phi equals beta, I know that it has to be periodic in phi, and the sine function is the most natural choice for satisfying this boundary condition. It cannot have a linear term in phi, because that will increase from 0 to beta. It cannot have a log s term, because log s term will not be 0 at s equals a. So, I can easily write that a is 0, b is 0, c is 0, d is 0, b m will be 0, and that is it. So, all I have left with this a m, c m and d m, and a m combined with c m and d m can be written as just two constants, and therefore, the solution is going to be v s phi equals summation m some constant a m s raised to k m plus Bm s raised to minus Km times sine of Km phi. That is specified by the boundary condition. You can calculate them explicitly and find those terms are 0. And since V phi equals 0 is equal to V phi equals beta, and this is all 0, so Km also automatically comes out to be m pi over beta. And therefore, I can write the solution V s phi as equal to summation m am s raised to m pi over beta plus bm s raised to minus m pi over beta times sine of m pi over beta phi. That is condition 1. Then I have that V equals 0 at s equals a, and therefore, I have 0 equals summation m am a raised to m pi over beta plus bm a raised to minus m pi over beta sine m pi over beta phi. This is true for all phi's, and this means that this term in the brackets should be 0 at s equals a, and this implies that Bm is equal to Am a raised to 2m pi over beta with a minus sign in front. And therefore, the solution for V s phi is going to be summation m. I can take out Am now and write s raised to m pi over beta plus, this will be the minus sign, minus a raised to 2m pi over beta divided by s raised to m pi over beta sine of m pi over beta phi, which can be written even more succinctly as summation m am a raised to m pi over beta in the brackets s over a m pi over beta minus a over s m pi over beta sine of m pi over beta phi. That is the solution. Now, AMs have to be found by the boundary condition on the other side. So, this is the best we can come up to with whatever information we have. So, for this problem, where I have been given that V is 0 at these surfaces, the solution V as phi is summation m am a raised to m pi over beta s over a raised to m pi over beta minus a over s raised to m pi over beta times sine of m pi over beta phi. That is my answer. Now, in part B, we want to find E phi and E s. So, the phi component of E is going to be minus 1 over s dV over d phi, and this comes out to be minus summation of m equals 1 to infinity, and then I have am over s a raised to m pi over beta times m pi over beta cosine of m pi over beta phi times this factor s over a m pi over beta minus a over s m pi over beta. That is E phi. So, you can immediately see that E phi at s equals a is 0. So, if you look at these surfaces, there cannot be any component of E in this direction parallel to the surface, constant potential surface. So, E phi is 0, and E phi at phi equals 0, that means on this surface, it has to be perpendicular. This is E phi, and this comes out to be minus summation over m and everything you write. I am going to take the lowest order term, and that comes out to be minus a 1 pi over beta s a raised to pi over beta, and inside I get s over a raised to pi over beta minus a over s pi over beta. And the field is in the negative direction, so the arrows I am making are given correctly. And E phi at phi equals beta comes out to be with a plus sign a 1 pi over beta s, and the rest is the same. That comes out to be going into the surface again. How about E r or E s? E s is going to be equal to minus d v d s, and when you do your calculation and keep the lowest term, you get E s at phi equals 0 and E s at phi equals beta to be equal to 0. Naturally so, because along these planes there cannot be any E s parallel to these constant potential surface. Only place where E s is non-zero is at s equals a, and that comes out to be minus 2 a 1 pi over beta a raised to pi over beta minus 1 sine of pi over beta phi, keeping the lowest term, and these are your answers. Then part C. Ask for taking beta equals pi, and that means your whole sheet becomes like this. This is a cylinder, and calculating fields. So, calculating fields far away, you will find that it becomes constant, and here the field will go like this, and calculate the corresponding charges on this cylindrical surface in the middle and on all the other surfaces per unit length. So, now once you find the fields, then sigma is very easy to find. It is going to be epsilon 0 E, and then you can integrate and find the fields. This part I will leave for you to do, and you will find that far away field is some constant E 0, and the rest of the problem you can do. So, this is complete the rest of the problem. I am going to do one more problem that is also taken from Jackson, and this makes use of the charge density. So, it will get you familiar with that also. This is Jackson problem 3.2. You are given a spherical surface with a hole on top, and this hole is in the shape of a cone with theta, the apex angle being alpha, and this rest of the surface carries total charge which is such that the surface charge density is equal to q over 4 pi r square, where r is the radius. And this is a hole on top. Do you recall a similar problem we had done earlier from Zangwill? Now, what you have been asked to do is show that the potential inside is V r theta equals q over 8 pi epsilon 0 summation L equals 0 to infinity 1 over 2L plus 1 P L plus 1 cosine of alpha minus P L minus 1 cosine of alpha r raised to L over r raised to L plus 1 times P L cosine of theta, and you are given that take P L minus 1 cos alpha equals minus 1 for L equals 0. And then they want you to find the potential outside and the electric field at the center. So, let us see how do we go about doing this problem. So, here is the sphere of radius r, and it has this hole of angle alpha, conical hole of angle alpha. I know from the expansion that V r theta, and this is azimuthally symmetric. So, V r theta is going to be given as summation A L r raised to L P L cosine of theta for r less than r. Why this? Because r less than r includes r equals 0, and this implies 1 over r raised to L plus 1 term cannot be there. That will make the potential blow up. And for r greater than r, V r theta is going to be equal to summation B L over r raised to L plus 1 P L cosine of theta. How do we find B L and A L? Again, we use the boundary conditions. What are the boundary conditions? They are going to be number 1, V is continuous across r equals r, and therefore, I am going to have A L r raised to L equals B L over r raised to L plus 1, or this implies B L equals A L r raised to 2L plus 1. That is number 1. Number 2, there is this charge density for theta from alpha all the way up to pi. So, the electric field E out, that is r greater than r, slightly greater than r, minus E in r less than r, is going to be equal to sigma over epsilon 0. Sigma is 0 for theta between 0 and alpha, and is equal to q over 4 pi r square for theta between alpha and pi. That is the other condition I am going to use. So, let us do that. V r theta is going to be equal to A L r raised to L P L cosine theta for r less than r and is equal to summation. Now, we have calculated B L also, which is nothing but A L r raised to 2 L plus 1 divided by r raised to L plus 1 P L cosine of theta for r greater than r. And we have sigma times is equal to epsilon 0 E perpendicular, that is radial, for r equals r plus minus E radial at r equals r minus. And that will give me the coefficient A L, because now we have only one coefficient left. So, this gives me that for theta between alpha and pi, I have q over 4 pi r square, epsilon 0 I can bring to this side, is equal to minus dV by dr calculated for r plus dV by dr calculated for r minus. That is this condition. And that gives me minus plus L plus 1 A L r raised to 2 L plus 1 divided by r raised to L plus 2 plus L A L r raised to L minus 1 P L cosine theta is equal to q over 4 pi r square epsilon 0 for theta between alpha and pi, and 0 for theta between 0 and alpha. And there is a summation L equals 0 to infinity. Now, I know what to do. I will multiply both sides by P m cosine of theta and integrate with respect to cosine of theta from minus 1 to 1. So, on the left hand side, I am going to get 2 L plus 1 was already there, A L r raised to L minus 1 integration minus 1 to 1, and there is a summation over L equals 0 to infinity, P L cosine theta, P m cosine of theta, d cosine of theta is equal to, on the right hand side, I am going to get from theta equals alpha to theta equals pi, q over 4 pi r square epsilon 0 P m cosine of theta d cosine of theta. Left hand side is quite clear. This fellow out here is going to be 2 over 2 m plus 1 delta m L. So, what I am going to get is two L plus 1 A L r raised to L minus 1 is summed over L times 2 over 2 m plus 1 delta m L is equal to q over 4 pi r square epsilon 0 integration minus 1 to cosine alpha P m x dx. Now, to integrate this, I am going to use a relationship. And that is what I had said earlier, that you need to use different recursion relations and things like those. And the relationship I am going to use is that dP L plus 1 over dx minus d by dx of P L minus 1 is equal to 2L plus 1 P L x. And therefore, this integral out here goes over to q over 4 pi r square epsilon 0, 1 over 2m plus 1 P L plus 1 cosine alpha minus P L plus 1 minus 1 minus P L minus 1 cosine of alpha plus P L minus 1 minus 1. Keep in mind that P L plus 1 and P L minus 1 are both either odd or even. So, their value at minus 1 are going to be the same. It is either plus 1 or minus 1, but the same. And therefore, this term cancels and you get the right hand side to be just q over 2 pi r square epsilon naught 1 over 2m plus 1 and the difference of these Legendre polynomials at cosine alpha. So, you get on the left hand side you get a m r raised to m minus 1 times 2 is equal to q over 4 pi r square epsilon naught 2m plus 1 times P L plus 1 cos alpha minus P L minus 1 cos alpha. And to be consistent, you take P L minus 1 cos alpha to be minus 1 for L equals 0. That you can check when you are doing it. So, I have got my A m, and therefore, the answer for A m is q over 8 pi r raised to m plus 1 epsilon 0, all this difference of P m, this should be m. To m plus 1, and that gives you the answer. In part B, find the field at the center. Now, you can see that by symmetry, there is going to be only r component. And what you need to do is calculate grad of V and put r equals 0. Therefore, only the term that is linear in R is going to contribute to field at r equals 0. So, only linear term in R in V gives E at 0. You keep only that term, you can actually write V linear term in R as a function of z alone, and then you can see that E is going to be minus dV dz, and this comes out to be something. It will come out to be in the radial direction, and that I will leave for you to do. I will now conclude this problem solving session by stating that we have solved 3 problems, 1 each in Cartesian, polar and spherical polar coordinates in 2D. By 2D, I mean where dependence is only on 2 coordinates. Thank you.